nanohub.org.
Other emerging dynamic atomic force microscopy techniques there are every day. Professor Raffenberger was just at the MRS meeting. I'm sure he heard about dozens of new scanning probe concept ideas. I will focus on three here, which I think are, some of the key interesting emerging things: high speed, multi-frequency, and subsurface imaging. Give you a brief outline of these emerging areas in AFM. Before we jump onto this, I think it's important to sit back and see, especially for those of you who have used AFM now, what are the driving forces? What is AFM as a technology evolving towards? What are AFMs going to be like 10 years from now? Hopefully not like what Fernando had to go through. Hopefully they're smarter somehow and easier to use. But what can happen? So speed is a very important one, and many of you would argue at the first glance that why is speed important? Because scanning speed is barely the main bottleneck as far as time taken to take an image is concerned for you, because it takes months to get an AFM to work properly and not crash the tip and all these things. Why are we so concerned about how fast it scans when it takes you months to come up to speed? There are many reasons for it. One reason is people who are skilled already in the use of AFM and want to study truly dynamic processes. So people don't want to just take snapshots, but let's say you're dealing with a problem where you want to take video images, where you actually want to see things moving at high resolution. How to do that. So and especially in biophysics, there's a lot of reasons for doing that. Things move under different, conditions. So there are certainly people with specialized interests in monitoring dynamic processes who need high-speed AFM. The second very simple need for high-speed AFM is that it's not a need, but it's a desire. What ends up happening is once you use a new AFM that scans very fast, you just don't want to go back to old low-scanning AFM. This is a very simple marketing thing. I'm telling you, people who do high-speed scanning and they come back and they take a line, it's taking its own time to scan, and you just don't feel like going back to your. So it's almost a psychological, it's the same reason why, people, the music format keeps switching from one digital format to another, and people switch because once you listen, it's better. Not that you need it, but high resolution, of course, is always important. The other thing is, it's very clear that people, when you're imaging now, you want everything from it. You don't want to just look at topography. You want to map every kind of property: electrical property, piezoelectric properties, thermal properties. Now everyone wants everything. Since you're taking an image, might as well get every property that you want, right? So certainly one sees this evolution towards almost information management coming from the amount at every pixel now. It's no longer just topography and phase. Now we've already talked of higher harmonics at every pixel. Now people are putting in piezo material properties at every pixel. People are putting in thermal properties at every pixel. So really, at some point, this is becoming a very big information management kind of exercise. But nonetheless, people are very interested in material contrast and improving it for different samples. And then some new needs are coming up. Certainly, subsurface information. Most of AFM measures on the surface. So in the early days, people are saying, hey, can we look below the surface? Instead of making a two-dimensional tool, can we make it a three-dimensional tool, high resolution? And then, of course, live cell imaging is important. Combined instruments where one tries to combine AFM with Raman and spectroscopy and things like that are very important as well. Give you an example of high speed. One of the leading groups is that of Toshio Ando's group in Kanazawa University. And this is an example of, they take images at 1 kilohertz plus per line. Most of you are probably doing it 1 hertz per line. This is 3 orders of magnitude faster. 3 orders of magnitude, 1 kilohertz per line. Or maybe more. This is more like, 1.25 kilohertz per line. So it's just 3 orders of magnitude faster. So it's video, basically. It's faster than video rate as it goes through. And they're able to, with that, they've done some spectacular work where they're able to actually observe the sequence of images. You actually see a protein, myosin motor actually moving its different domains and walking along a microtubule. You can actually see these motors moving their legs, so to speak, and walking. Amazing stuff as far as biology is concerned. The key question is what technology actually enables this? They use high bandwidth scanners. The scanners need to be able to scan at very high frequencies now. So you need high bandwidth scanners. You need high bandwidth Z piezometers, because Z piezometers now need to respond very fast to go up and down as you're going up and down really fast. You need fast phase detection, you need small cantilevers because you want the cantilever frequencies to be very high. And so people use extremely small cantilevers for this that are 20 microns long now. And 20 microns long. So the length of the cantilever we're used to is 200 microns long. Now the length has become 20 microns long in these. So new AFM technologies are now allowing you to focus on really ultra small cantilevers because they have very high frequencies. So these cantilevers have nearly a megahertz frequency. Now, that's happening. People are using different excitation mechanisms that allow you to excite these cantilevers at 1 megahertz, and so on. So there are a lot of interesting results with high-speed AFM. Again, on the top left, more results from Anda's group. I want to bring to your attention the work out of Merv Miles's group at Bristol. They came up with a very different AFM idea a long time ago, where they put a tuning fork as the sample scanner. So the sample would be placed in a tuning fork, and you'd vibrate the tuning fork at 32 kilohertz. That's your scanner. So the scanning rate is 32 kilohertz per line from the get-go, because the tuning fork is oscillating at resonance, right? And of course, at such high speeds, you can't get cantilevers to do feedback control when you're scanning so rapidly that, So they decided to do sort of an open loop kind of. Initially, they implemented like an open loop where it's contact mode, but instead of keeping deflection constant like we do with the help of feedback, it's scanning so fast, they just keep the Z constant and they just let the cantilever deflect up and down, like what you were mentioning, Fernando. And the reason why, one, it worked is it's happening so fast, so there's very little time for thermal drifts. There's 32 kilohertz. They're done scanning. Like, you just snap your fingers, that's the time it takes to pretty much scan over that fast, because they're doing video rate much faster than video rate. So there's no time for thermal drift, so you can afford to do that if you go very fast. But the flip side is, in contact mode, you're applying a lot of lateral forces. You're also rubbing. You could be damaging things by continuously scratching back and forth, right? So how do you avoid that? Well, they haven't completely figured out the reasons for it, but they've figured out that what happens is when you start going fast laterally, they're saying that there's an interesting, like a hydroplaning effect that happens, because under ambient conditions, there's always like a layer of water present in everything. They found evidence that you go very fast and there's a little lift off. The tip lifts off a little bit as you go very fast. And this is what happens, for example, in hard disk drives. In hard disk drives, you don't want the read-write head to be scratching against the surface. So how does it raise up by 2 nanometers? It's hydrodynamics. It's just you spin very fast, a thin wedge of lubricating air forms, and it just lifts it or separates it. And so they think that's what's happening in the AFM at high speed, is this lifting up effect, which allows you to scan at high speeds without damaging biological samples. Multi-frequency AFM is also an interesting area that's evolving quite a lot. And what happens in multi-frequency AFM or bimodal AFM is, instead of driving just one eigenmode, you do the tuning curve and you get 2 resonances. Well, you drive both resonances simultaneously. That's an interesting area of research. And it turns out that now you not only have amplitude and phase of the first mode, you have amplitude and phase of the second mode while you're scanning the sample. And it turns out that you can show that while the phase of the first mode, or the sign of the phase of the first mode, is connected to dissipation, the sign of the phase of the second mode, or even the virial of the second mode, are now connected to a mix of conservative and non-dissipative properties, right? But the key thing is that because they involve mix of conservative and dissipative properties. So let's say you're imaging a sample in the attractive mode. So you don't want to touch the sample. You're in the attractive regime. So you're not physically tapping, right? And yet you want to see some material property contrast. What do? Is the question, right? Because remember, phase contrast is most likely to happen when you dig in, tap in. There are some exceptions to the rule, which Hank is going to present in his stuff. But if, under most circumstances, when you're tapping on a sample, is when you get phase contrast. If you're not touching, there's very little energy dissipation, and so you don't see much contrast. So the trick is, how do you get material property contrast when you're in the attractive regime? So Ricardo Garcia's group in Madrid came up with this idea to try and, this is a possible advantage of using two eigenmodes, where you can then, because the phase of the second mode depends on conservative interactions, that means that even when you're in the attractive regime, you can get contrasts of these conservative interaction properties. They've shown many examples in liquids also. For example, let me show you an example. This is out of Asylum's research. I want to point out something very important here. Figure 2 here on the left shows topography of freshly cleaved graphite. B is the amplitude of the fundamental, which is supposed to be constant. Right? So they point out B is the fundamental amplitude channel used for feedback error signal. So here they don't plot it. They clearly say that they demonstrated as an example to show how nice they kept the amplitude constant, right? So they show figure 2B. I really want you to take a look at this. It's very important because that's how you use the error signal. Figure B is a map of the error, of the amplitude over the sample. What they show by showing a length scale on the side is, as you scan over the sample, the amplitude did not change more than 2 nanometers. That means it's a pretty good control. It's only at certain edges that it wasn't controlled, but they kept it pretty constant as best as possible. That's how you use this information, The other thing is, in figure C, you see phase lag of the first eigenmode. Again, notice that in C, they very clearly say phase lag in degrees. Very few people plot phase maps and say that it's phase lag. Most people just say phase. Well, and I hope you understand now that depending on whether you call it phase lead or lag, what's bright, what's dark, flip. So they take the effort to say it's phase lag, and they point out it's 34 degrees, indicating that the cantilever was in repulsive mode for the entire regime. I mean, that's the way you use it, right? So you scanned over the sample. Over the entire sample, the phase lag image is 34 degrees. So it's below 90 degrees, which means over the entire sample, you're tapping. So now that's the way to use this information, right? Say it's phase lag, say what the value is, it's below 90 degrees, so it has to be, that's good stuff. Nonetheless, what they found is when you look at D and E, so C is the phase lag, and it wasn't showing much variation. You see, it shows just a couple of degrees variation over the sample. But when you look at the phase of the second eigenmode, it shows this amazing contrast that's shown here. Black and white regions completely different. Of course, the reason for it is well known. Why after all, it's graphite. Why do you expect contrast? Well, it's known in graphite, as soon as you peel graphite, you start getting impurities that start depositing on the graphite. And for some reason, which I haven't understood completely, but the deposition of, maybe Ron can shed light on it, deposition of these materials on HOPG, they go flake by flake. It's very domain connected somehow. It's not like you would expect like powder falling everywhere, but it seems to, the impurities seem to fall on one flake of graphite at a time. They somehow don't all uniformly spread. I don't understand this myself very well, but it's known that you start getting these regions that start getting impurities collecting on it. And so what you're observing is effectively that it's, they end up saying that it has to do with this process where patches of HOPG start getting impure because as you expose it in air, hydrocarbons just keep attaching themselves to the substrate. So that's the source. And of course, they've done DNA as well and shown some high contrast. So this is an interesting area. Let me tell you about subsurface imaging. a little bit about subsurface imaging, and we'll end with that. Currently, the most important way of doing subsurface imaging is the following. Here's what we're trying to do. We have a sample, and then underneath the sample, at some distance beneath the sample, we've got some inclusion. And we want to see that inclusion. We want to go beneath the surface and see things with an atomic force microscope. This is the very interesting question, how do we do it? And the current techniques that are out are based on heterodyning principles and principles that come from much older, the acoustic force microscopy and AM radio signal ideas. You know, it's interesting how people have combined these ideas. But going back to while at Oxford with Briggs and Teresa Kuberis and Kolosov, they developed these ideas of heterodyning, right? They did not develop subsurface imaging, but they developed this idea that, let's say, most of AFM we're trying to map a surface that's not moving. The surface is fixed, right? It's not moving. But what if we make the surface vibrate at a very high frequency? Can AFM be used to map the amplitude of vibration of the surface? That's the question. And they figured out an interesting way to do that. And then later, when Vinayak Dravid and later Ali Pasian and Oak Ridge, they sort of pushed this effort to use this principle to image subsurface features. So this is how it works. What you do is, on the left, you apply beneath the sample a very high frequency piezo excitation. Okay? Fs in megahertz. Right? That's how they did it. And we'll examine what the positives and negatives of it is. So you apply very high frequency vibration beneath. That vibration is going to transfer to the top surface somehow, right? So the top surface is also going to vibrate at a frequency Fs, right? Because you're shaking it from below. It's a forced vibration problem. So top is also going to vibrate. The only thing is the amplitude and phase of vibration, the frequency is the same as Fs, but the amplitude and phase of vibration are now going to start depending on whether there was an impurity between the point where you launched the high frequency excitation and the surface. So you can imagine that if you have some impurities in between or some dislocations or some other insert of some sense, it'll influence in some sense the propagation of this high frequency acoustic wave to the top. The frequency has to remain the same, but it might change the amplitude. This is the basic idea. So if this is the idea, then suddenly, in order to see this subsurface feature, what we want to do is not map the topography of the top. What we have to now do is map this amplitude and phase of vibration on the surface. If we map that, so now we got a vibrating surface. Now we're not going to measure topography. Now we want to use the AFM to measure how is it vibrating more here or less here. If it's vibrating less, maybe there's something underneath us. And map it. So then you can do maps. How they do that is interesting, because when you apply megahertz frequencies, the cantilever isn't going to respond to such high frequencies. So what they do is they put an AFM tip on the surface. You've launched this frequency F. So the surface is vibrating at Fs. They apply another frequency to the cantilever, FP, another high frequency excitation. So the sample is excited at, let's say, 1 megahertz. The cantilever is excited at, let's say, 1.1, slightly different frequency. So now what ends up happening is the tip sample gap, the sample is moving up and down with 1 megahertz. The tip is moving up and down with 1.1. So what happens to the interaction forces? And remember, the interaction forces are nonlinear. And nonlinear interaction forces produce higher harmonics. We already talked about that. Well, when you have two different frequencies, Fs and Fp, it turns out the harmonics you get out of it are now not only higher harmonics, but there are also difference and some harmonics you can get in the interaction forces. So the difference harmonic, that's the difference between Fs and Fp, is small, because one is 1 megahertz, the other is 1.1. So the difference is a small frequency, and that you can pick up in the cantilever. And that's what they do. They lock into the difference frequency and map its amplitude and phase over the sample. That's it. And they prove that with that, they're effectively mapping the amplitude and phase of the surface vibration. This is the basic idea. Yeah?
It's not that the problem for high speed IFM because
Yeah.
it's like an ultrasound test. So at the end you are tapping very fast and you're measuring the waves in the depth.
Yeah.
So in high speed AFM you are tapping very fast.
Well, I mean, obviously there's.
So your image will be giving you
Well, so this.
things.
Yeah. Well, I mean, of course. I mean, one has to. People don't do high speed with this, right? So.
No, but in high speed you are going very fast.
Yeah.
So you are providing waves.
Oh, we can talk about that later. See, we can talk about that a little later. It's a good point. But I think the samples are usually deep enough that it's time enough for everything to settle. I think so. But let me show you results, right? This is from the original paper by Shekhawat. They've started a company up in Chicago that runs this. But what you see on B is, so the sample is gold particles coated with polymer. B is the topography on the top. C is this difference frequency phase image where you see the underlying particles that are buried 500 nanometers beneath the surface, right? And then they started doing it for many different samples. Here, for example, they're doing red blood cells, and they were able to see internal features coming through that, right? More recently, this is extended to live cells in air, though, but what they did is topography is A, and in B, they're looking at this difference frequency phase. And what they did in the cells, this cells is they fed effectively, or they injected these carbon nanohorns into the rat. They wanted to see how nanoparticles propagate through the body, and so they found these nanoparticles collected inside the cells. They extracted the cells, imaged it. They wanted to see where are the nanoparticles inside the cells. Well, they do this subsurface imaging technique, and they find the black dots are where the nanoparticles are collecting inside. So remember, the cell is 2 microns high. So here they're basically seeing features that are 2 microns beneath the surface. So what are the challenges with this method? Unfortunately, we still don't know very well the mechanism of image formation, because how is it that you're able to launch 1 megahertz wave? 1 megahertz wave has a wavelength of 100 microns or something. How come you're seeing 20 nanometer features with sound waves that are microns? That still is not clear at all why it happens. They're getting results, but we don't know very well what they're saying. Second is, we would love to know how deep these objects are. You see them, but can you tell how deep they are? Because if they're deep, then you can start, if you know the depth, then you can start doing true 3D reconstruction of full 3D maps, if you know how deep it is. How do you know how deep it is? They don't know. So this is a very interesting area. So these are some of the 3 key areas where AFM is advancing, and I'd like to end the lecture with that.